as our example, we will take the field from a so-called dipole. So for the field of a dipole, let me just write down what we're doing here, right? Field of the dipole, and I'm going to use the field line, FL representation for it. And what a dipole is, it's two equal but opposite charges placed in proximity to one another. So I'm going to have a positive charge here plus Q, and then near it somewhere I'll have a negative charge with exact equal compensating charge minus Q. And our job now is to try to construct the field lines for this particular situation. Now remember the analogy that we're going to be using. The analogy says, let's set up what we would expect in water world to be the exact analogy to this. So I'm going to put then 2 point sources in the fluid. One represents a charge plus Q, and we know, in fact, how to set up such a point source, right? We'd have a little sprinkler ball, and we'd be pumping current into that ball from out here along some hose, and that then, of course, would result in fluid flowing out from there. Over here we have a negative charge. We haven't discussed this in a tremendous amount of detail, but the way you construct the analog to a negative charge is fairly straightforward. For positive charge, you're pumping fluid in to this sprinkler ball, which then has fluid then oozing outwards in all different directions. For a negative charge, the electric field doesn't point outward, right? The electric field points inward. And the way we accomplish that, the opposite of pumping a fluid, a current, down a hose, is to actually pump the fluid out of the system through a hose as well. That will then suck fluid into this source, drawing it inward, making an inward velocity, which in electric world would correspond to the correct inward electric field. So this is what we're setting up. So we imagine putting this device into some large tank of water. We let that flow pattern settle down, and then to trace out the field lines, we're going to think about what happens to little particles that are injected into the fluid. So we can imagine putting a little tracer particle right here at this corner, right? And we're going to ask, what do we think the history of that particle is going to be? Well, very clearly, it's being repulsed and ejected by my positive source, and it's going to be pulled into this negative source, sometimes called a sink, by the way, in fluid mechanics. So this tracer particle, I would imagine, right, would simply go straight across from my positive source and get sucked into my negative source. And that, in fact, is our first correct field line. Let's imagine then what would happen to the particle that's, ejected here, say, at 45 degrees. Well, what will happen to him is, of course, initially it's going to be pushed directly outward from that point. But as it begins to move outward, right, it starts to feel the sucking from this particular sink. And notice that we are pumping in exactly the same amount of fluid on this side as we are sucking out on this side. That means that each and every drop of fluid that comes out of this plus Q source has to be sucked in to the minus Q source. So this particle is going to come out of the plus Q, but then eventually he's got to arc around and get sucked into the minus Q. And I'll try to draw this so it's nice and symmetric. So his path will be something like that. And always be sure to make these directed lines. So I'll need an arrow like so. Well, we can continue this pattern. The particle that starts out on the top here, right, again, initially it's going to be ejected, but it has to eventually wrap around in order to get pulled into that negative charge. So I don't know, it might do something more like this. I tried to make that look symmetric. It came out sort of okay. Even the one that comes out at this angle eventually has to get sucked in. So it's going to have some path where first it kind of goes away, and then it starts to feel the sucking. It's going to arc around and come in on the other side. I don't want to draw a super large arc, right? You can imagine that it's going to be connected in the other regions of my diagram. It's coming out here, and it's coming in there. Now there's one tricky case. that's the particle that's ejected on this side of my source. In that case, if he's exactly on the line, right, he has no reason to decide whether he should arc around up or if he should arc around downwards, right? Now, in real life, of course, nothing's exact to the size of a molecule. The molecules coming out of here will always be on one side or other of the pattern. So in real life, every particle coming out will eventually arc around and get sucked back in. But there's this one mathematically abstract case, right, of the one that comes out exactly on this side. And because it has no reason to go either up or down, it actually can continue directly outward forever. Now, if you want to think about it this way, you can. You'll notice there's a corresponding other side of this line. It goes out to infinity, but then on the other side, it has to come in from infinity, right? There's another line that looks like this, where particles are exactly on this boundary between up and down, and so they just kind of come directly straight in to my sink like that. Okay, now that's the top half of the pattern. We can complete the pattern. It basically, you can see, it's very symmetric. It should be symmetric down below. The one that comes out here, 45, should come in like so and line up. This one here should kind of look like the line up above, which I'm always having trouble making come out just the way I might like it, maybe something like so. And then the 45-degree one's going to arc around here, and it's going to have to eventually, come back in on this side like so. And in fact, it turns out that that will be exactly the field that we would expect, the field line pattern, the field line representation of what we would expect for a dipolar situation.